Hi everyone. In this video, we will continue the discussion of uniformly accelerated motion. Uniformly accelerated motion. Okay. So let's discuss a few points regarding uniformly accelerated motion, and then we will use or apply this theory for the case of uh, a body falling under gravity, which would basically be uniformly accelerated motion, and later on we would discuss some other examples, okay, in the form of problems and all. Okay, so when do we say that a body is moving, or when is a body is said to be having uniformly accelerated motion? So we say it's uniformly accelerated if acceleration of body is basically constant. So basically, if it has same magnitude and direction, okay, or if acceleration doesn't change with time, then the body is said to have constant acceleration, or in that case it is said to be undergoing uniform acceleration. Okay, let's say that constant acceleration is given by a. So if acceleration is constant, then basically a few equations we can get, okay, connecting velocity, displacement and acceleration. You already studied those things, okay, in the first year from the NCERT book. Briefly I will try to discuss the derivation of those again mathematically, okay, not graphically. Earlier you have studied graphically, now let's do it mathematically. So acceleration is constant, we can write it as a is equal to dv by dt. dv by dt represents rate of change of velocity. So dv would be basically a into dt. Okay, so dv represent infinitesimally small change in velocity during the very small interval of time dt. So where a is the acceleration at that instant. So let's say we wish to calculate the change in velocity of the body during the interval of time t1 to t2. Okay, let's say at t1 the velocity is given by u, or initial velocity is u, at, or let's call it v1 itself. Okay, so at t2 the velocity is given by v2. We know that integral dv is nothing but v2, so which would be equal to, so we already imagined a situation where acceleration is constant. So since a is a fixed quantity here, it can be brought outside the integral. So we would get integral a dt t1 to t2. So what we would get? So if we substitute upper and lower limits, we would get v2 minus v1 is equal to a into integral dt, basically mathematically equal to t, and the upper limits and lower limits are t1 and t2. Now if we apply them, if you substitute upper limit and then lower limit, so t2 minus t1 basically represents the time interval, okay, whatever you are considering. Let's say we assume, okay, the t1 is equal to 0, indicating the initial instant of time from where you started observing the motion of the body. Then v1 would be the initial velocity. Let's represent it with u, and let's call t2 as t, okay, and v2 at that particular time t, or after a time t from the start of the motion, v2 is equal to t. Then if we substitute those things, we get v minus u is equal to a of t2. I'm writing the basic same equation again, a of t2 minus t1, which would be t, or we can write v is equal to u plus at. So this is what velocity of a body v is going to be after a time t, if it's moving with a uniform acceleration or a constant acceleration. Okay, now let us try to get the relation between the displacement and time. Okay, so we have the relation, the connecting v and s, which is nothing but v is equal to ds by dt. or we can write it as ds is equal to v into dt. Okay, so again, if we integrate it, or let's say my interest is to find the displacement in the first t amount of time, then if my interest is to find the displacement in the first interval of time t, then what I would consider the limits to be 0 to t. So during that interval of time, okay, the t is equal to 0, as we have discussed earlier in the graphs, the displacement would be 0. Then let's say after it in time t, the displacement is s. So integral ds would be s, which is equal to integral v. V represents velocity at any random time t. So as we got earlier, v after a time t can be written something like this: u plus at dt 0 to, okay, better to avoid confusion, let's take this as t1. So we want to find the displacement in the interval 0 to t1, where t represents the time at any random instant. Okay, then u plus at would be the velocity of the body at that particular instant of time t. So s is equal to, so we can basically break apart this integral into pieces. We would get integral u dt 0 to t1 plus integral at dt 0 to t1. So first integral, if you observe, this u can be brought outside because u represents initial velocity, so that is basically fixed. Integral dt 0 to t1 plus, here in the next integral a is a fixed quantity, so I can basically bring it outside, t dt 0 to t1. So that implies s is equal to u integral dt would be t, so it would come out as u t1 plus a into integral t dt would be t square by 2. The limits are again 0 to t1. That's nothing, that's a mistake. So we would get s is equal to u t1 plus, again if we substitute the limits there, we would get it as half into a into t1 square. So if the body starts moving, or let's say if the motion is started being observed from t is equal to 0, in the first t1 amount of time, the displacement would be u t1 plus half a t1 square. Our displacement would be equal to, in the time t, ut plus half a t square. Basically that's what the displacement would be in a time t. Okay, now using these two relations, whatever we just got, s is equal to ut plus half a t square. Let's call this first and let's call this the second one. Okay, now just make one small observation. I mean, if we use both of these two things and we get rid of time t, we would basically get v square minus u square is equal to 2as, another relation. Okay, this relation we can obtain from the one and second equation by just getting rid of time t, third relation. Okay, now one small observation from here which I would like to conclude: v square minus u square can be written as v minus u into v plus u is equal to 2as. So v minus u is basically at into v plus u, which is equal to 2as. A gets cancelled, so we can basically write it as v plus u by 2 is equal to s by t. So if you observe here, the right hand quantity of that equation, on the right hand side we have displacement by time. So as we discussed earlier, the displacement by time would give us the average velocity during that interval of time. Okay, so basically if a body is moving with a uniform acceleration, okay, then the average velocity during interval of time t would be v plus u by 2, where u is the velocity at the starting of that motion and v is the velocity, final velocity after a time t. Okay, so average velocity is u plus v by 2. So in some problems basically this relation would quite be helpful in order to make the calculations. Okay, for example, let's say they gave you a problem something like this. Let's say a body is undergoing uniform acceleration. Okay, uniform acceleration for a time, let's say 2 seconds, where at the start of the motion velocity was 4 meter per second, and at the end of the motion or after 2 seconds its velocity is 10 meter per second. In this interval acceleration is constant. Now if you wish to find the displacement in this case, displacement during this 2 seconds of time, okay, the easy way is you just displacement we can write average velocity into time. Since we told that the body was moving with a constant acceleration, average velocity would be u plus v by 2 into t. So our 4 plus 10 by 2 into t would basically be 2 seconds, which would come out as 14 meters is the displacement. The calculation is quite easy because we used the average velocity relation. If you didn't know that relation, then how we can solve this problem? If we don't know, first we have to find acceleration. How do we need to find acceleration? By using v is equal to u plus at. Once we calculate acceleration, then we can use the relation s is equal to ut plus half a t square. So basically here we have to make two calculations to find displacement. But if you knew the relation for average velocity, you only need to make one calculation in order to get the answer. Okay. Now the other relations that are valid for a body under uniform acceleration would be, I will be basically writing them here. Okay, let me write all the relations that are valid. V is equal to u plus at, okay, s is equal to ut plus half at square, and then average velocity is equal to u plus v by 2, v square minus u square is equal to 2as. This same displacement relation we can also write it as vt minus half at square, where v represents the final velocity. This would basically be helpful when we know the velocity at the end of that time interval instead of the velocity at the beginning. And the other relation that we can write is displacement in nth second. This is basically displacement in nth second. So this would be u plus a by 2 of 2n minus 1. Okay, so all these relations that we have written now are only valid if the body is moving with a uniform acceleration, or it is said to be accelerated uniformly. Okay, now let us try to draw the graph of displacement time graph, velocity time graph, and acceleration time graph for a body moving under uniform acceleration, or if it's accelerated uniform. Okay, now let's continue. Let's try to draw the graph. First, okay, let's take a simple scenario where the body is moving with acceleration is constant, but let's assume a simple case where initial velocity was 0. I mean, even if the initial velocity was not 0, the method of drawing the graphs will still be the same. It doesn't change. Okay, there would be a minute variation. That's it. So now how would the equations come out to be? Then velocity would be a into t, I mean velocity after a time t, and displacement would be half into a into t square. So first, if we try to draw the graph of displacement versus time t, so as you can see there, the relation displacement is proportional to square of t. So basically the graph would be something like this. Okay, so it's not a linear relationship between s and t. So what we basically get is a parabola. Okay, because here s is proportional to t square. Okay, as we already know that A is fixed quantity, so we can say this is proportional to t square. Then if we want to draw velocity time graph, how is it going to be? So if velocity time graph, if you want to draw, first look at the mathematical relation. Since A is constant already, then we can say proportional to t, because A is basically not dependent on time, it's invariable. Then since you have it something like v is equal to at, it's similar to y is equal to mx. Okay, in the place of y we have velocity v here, and in the place of x we have time t. So then the graph would basically be a straight line, okay, because v and t have a linear relationship. And next thing, if you make another comparison here, in the place of slope m we have acceleration. So if this graph was making an angle theta with the horizontal axis, then that tan theta, which is the slope, would basically be the acceleration of that particular body. So one point to remember, if the body is moving with uniform acceleration, velocity time graph would basically be a straight line, where the slope of that straight line gives us the acceleration of the body. Then how will the acceleration time graph is going to be? So since acceleration is constant, so at any time t, the acceleration does not change with time. So the graph would basically be something like this, where the graph would be perpendicular to the acceleration axis. Okay, it would intersect the acceleration at a point which has a value equal to that of the acceleration. So this is how the graphs are going to be. Okay, what if the initial velocity was not zero? How the graphs would basically look like? Okay, so let's say we had a case where initial velocity was 2 meter per second, something like that. Then both displacement time graph and acceleration time graph, acceleration time graph would be same, displacement time graph would vary a little bit, okay, but still it would be a parabola itself. In that case, the displacement relation would be 2t plus a by 2 t square. Still it would be a parabola. But the major change that we observe is in the velocity time graph. So velocity time graph would still be a straight line, but with a minute variation. The variation is, now earlier when the velocity was zero, it was passing through the origin, or it was intersecting the velocity axis at zero. Now it would be something like this. Okay, so it would intersect at 2, and if the same acceleration, the slope would still be the same. M would be equal to tan theta, which would be the acceleration of the body. So this is how the graphs are going to be in the case of uniformly accelerated motion. Okay, now let's try to discuss a few simple example problems related to, what do we say, the graphs and as well as the uniformly accelerated motion. Okay, first let's discuss one or two examples based on graph. Okay, let's say we have position time graph, something like this. Okay, let us consider 2 points. Let me call it A. Let's call another point B. Let's call another point C. So one small point here, not able to represent properly. So imagine that point C is at the topmost point, okay, or until point C the position x value has been increasing. Beyond point C the x value is starting to decrease. Now let's say they asked you a question something like this. So what we can conclude about the motion of the body at point A corresponding to point A? Let's represent some times corresponding to them. T1, T2, T3. So at time T1, what we can comment about the motion of the particle. So if you look at the graph at time t1, okay, so let's draw a tangent. If you look at that tangent, basically here, okay, so let's say the tangent makes an angle theta 1 with the horizontal axis or the time axis, then the slope of that would be equal to the velocity corresponding to the point A, or velocity of the particle at time t1. You see there, the theta 1 is basically acute, so tan theta 1 would be positive, so that means the velocity would also be positive. So positive velocity indicates that it's moving along positive x direction, or we can say that the x keeps increasing. As you see the graph, okay, the x is continuously increasing until time t3. Now look at the point B. Okay, so what we can conclude about the motion of the particle at time t2. So for that, let's draw a tangent here. So if you draw the tangent there, okay, now if you make proper observation regarding the angle made by that tangent with the x-axis, that angle is basically obtuse. Then as we know, if angle is obtuse, if angle lies between 0 to 90 degrees, then tan of such an angle would be negative. So what we can conclude, VB is equal to tan theta 2, so which would basically be negative. Okay, so that means at point B, velocity of body is negative, which means that it was moving along negative x-axis. So if it's moving along negative x-axis, which means its x position or x coordinate basically keeps on decreasing. That's what you see there. Okay, so in that right portion of the graph, x is basically decreasing. That's clearly visible. Then what we can conclude about the motion of the particle at point C. Okay, so until point C, the position x has been increasing. Beyond point C, to the right of C, the x started to decrease. Now C is kind of a maxima corresponding to that graph. So as you already studied in math, that for a graph at maxima or minima, if we draw a tangent, okay, the tangent doesn't seem to be kind of a tangent, but just adjust with it. So the tangent would basically be parallel to the horizontal axis. Then if it's parallel, if a line is parallel to the x-axis, slope of such a line will be equal to 0. Then so velocity at point C would be slope of that line, which would be basically 0. Okay, because theta would be 0 in that particular case, tan 0, 0. So at point C, at the point where the position seems to be kind of locally maxima or maximum, the velocity at such point would be 0. Okay, the same thing we will observe if you had a situation something like this. Let's take another graph. Okay, some random graph. Okay, I'm not saying that it's a sine graph, it's just some random graph. Now if you look at 2 points, okay, corresponding to t1 and t2. At t1, if you observe, it's maxima, there slope would be 0, and at t2 it's minima, here also slope is equal to 0. One important observation that we need to make here is that, so if you look at the part of the graph just before t1 and the part of the graph just after t1, until t1 x has been increasing, after t1 x started to decrease. So until t1, I mean, we are only looking at the portion of the graph which is very close to the time t1. So basically until t1, the x position has been increasing, which means it was moving in the right direction. So beyond t1, the x position started to decrease, which means it started to move in the left direction. So basically until t1 it was moving in the right, after t1 it started to move in the left. So we can conclude at time t1, the direction of velocity or the direction of motion has basically changed. Okay, the same thing we can say here also at time t2. So until t2, you see the x kept decreasing. Okay, beyond t2 x started to increase. So what I can say, until t2 x kept decreasing, so the particle was basically moving along negative x-axis. Beyond t2 x started to increase, which means it started to move along positive x-axis. So basically the direction of motion has changed, or change of the direction of motion has occurred at t2 where velocity is 0. Or the final conclusion that we can make here is that, so wherever the direction of motion of a body along a straight line changes, at that instant or at that particular point the velocity would be equal to 0. Okay, so if you wish to calculate, or if you wish to determine, okay, if the direction of motion of a particle is changing, then focus on the velocity of the particle. Okay, just see if there is any time, instant or position where velocity is 0. That's where the direction of its motion would basically be changing. Okay, now let's continue. Okay, and just to see here. Now let's say we have a case where acceleration and velocity are in same direction, a and v in same direction. Let's take a simple case so that we would understand it better further. Okay, let's take a case where the body was moving in the right direction. If the body is moving in the right direction, means velocity would be positive. Okay, one small point here, the velocity depends on the direction of the motion. Acceleration direction does not depend on the direction of the motion. It depends on the rate of change of velocity. It depends on how fast the velocity is changing with time. It doesn't depend on the direction of motion. So what do I mean by that? We'll understand that in the next example. See, let's say velocity is positive, acceleration is also positive. So if I say velocity is positive, which means that the body is basically moving along positive x direction, then what does acceleration being positive mean? Okay, acceleration positive, that means the body is being accelerated along positive x direction. So what I mean by that is, okay, so if acceleration is positive, okay, we know that acceleration is rate of change of velocity. So the rate of change of velocity can either be positive, 0 or negative. So the rate of change of velocity would be positive when v is increasing. Okay, the acceleration would be 0 when v is constant or it's not varying, or acceleration would be negative when the velocity is basically decreasing with time. Okay, so positive value of acceleration indicates in this particular case that the velocity of the body is basically increasing with time. Okay, or we can say that the body, I mean, if both are positive, which means both are in the same direction, then in such a case the body is said to be accelerated, or its velocity will keep on increasing if both are positive. The same explanation can be valid if both are negative as well. Okay, so if either both v comma a positive or negative, that means when both of them are in the same direction, that is in the right direction, or both of them are in the left direction, the body would basically accelerate. Okay, suppose let's say we have a scenario where one is positive and the other is negative. Let's say something like this: v is positive, acceleration is negative. Acceleration would only be negative when velocity is basically v is decreasing. So if V is decreasing, the body is basically said to be undergoing deceleration or it's undergoing retardation. Okay, so in this case, okay, with time the velocity of the body keeps decreasing. Okay, so we can say, simple terms, everything put together, we can say when both acceleration and velocity are in the same direction, the body will accelerate, velocity will increase with time. If velocity and acceleration are in opposite direction, then the body will kind of slow down or it would undergo deceleration. That's the conclusion. Okay, so we are going to use this point, okay, for studying the motion under gravity, which we'll be doing later. Okay, now let's discuss a few example problems based on uniformly accelerated motion. Okay, let's say you have example something like this. Let's say they gave us the acceleration time of a graph of a body is something like this. Okay, let's say acceleration is 4 meter per second square. Okay, everything is represented in SI units, so I wouldn't be representing the units basically. Now our intention is to calculate the change in velocity of the body during the interval of time 4 to 8 seconds. So the change in velocity during interval 4 to 8 seconds would be area under the graph, which would be, this would be 4 units and this would also be 4 units, which would be equal to change in velocity V8 minus V4, which would be equal to, so what would that be? 16 meter per second. The same thing we can get from the equations as well. Okay, so velocity V8, velocity after 8 seconds is initial velocity plus acceleration into time. Okay, then what about velocity at t is equal to 4? Basically I am using u plus at here in these relations because acceleration is constant, so I can use them. U plus acceleration into time is 4. Now if I do V8 minus V4, I would get u plus 8 into 4 minus of u plus 4 into 4. So this would be equal to 4 into 4, which is equal to 16 meter per second. The same answer as we got graphically. Okay, now let's take another example. Okay, let's say we have a graph something like this. Let's say they gave us velocity time graph of a body okay, I'm considering again SI units 4 6 8. Okay, so this is a negative velocity of, let's say, 1 minute 4, this would be minus, the graph didn't come out to be good. Just 1 minute. So this is the velocity at t is equal to 8 seconds. Now they can ask any number of questions from here. So let's say we want to calculate first displacement, okay, between 0 to 2 seconds. So how do we calculate displacement? Displacement from velocity time graph would be area under the graph. So if we want to calculate the displacement during that interval, so I will draw the part of the graph separately to calculate the displacement. This is what that part would be. So this would be 2 units, this would be 4 units. Basically this would be that area. This area would numerically be equal to the displacement during that interval of time. So which is equal to, the area would be half into base into height, which is equal to 4 meters. So that's what the displacement is in that 2 seconds interval of time. Now let's say our next target is to calculate displacement in the interval of time 0 to 8 seconds. Now if you look at the interval between 0 to 8, you have the section of the graph, okay, a part of the graph above the time axis where velocities are positive, that is between 0 to 6, and you have other section of the graph 6 to 8 where the velocities are negative. Now the total displacement that I have here, I will split it into parts, to calculate the areas. So the total displacement would be area under the graph. So we will calculate area from 0 to 6, because between 0 to 6, if you look at the area below the graph, it would be basically a triangular portion, plus again displacement from 6 to 8. So displacement from 0 to 6 is given by, since it's a triangle, half into base is basically 6 units, into height is basically we have from here to here, which would be 4 units, plus the next question that we need to take here, between 6 to 8 seconds, okay, if you look at the area is below the graph, or where the velocities are negative, hence that area should be taken as negative. So half into, okay, next this side length would basically be 2, this side length is also 2. 1 minute, we have to consider minus here, I made a mistake. Half into 2 into 2, which would be 12 minus 2, which would be equal to 10 meters is the displacement during that particular interval. Okay. Now what we can comment about acceleration of the body during that whole interval. Okay. So we can conclude that it is not uniformly accelerated motion, because if it was uniformly accelerated motion, it would be a continuous single line. Okay, you might think that here it's a straight line, so it's uniformly accelerated, but it's not. So from 0 to 2, it's one straight line, it's along one direction, but between 2 to 8 seconds, it's along another line. Okay, basically slope of the portions between 0 to 2 and slope of the straight line between 2 to 8 is different. So hence acceleration in this 2 interval of time would also be basically different. Okay, so 0 to 2 seconds, how do we calculate the acceleration? So acceleration 0 to 2, see, since it's a straight line, okay, the slope at any point you consider on the graph between 0 to 2 would be same, which would be equal to the slope of this particular line. Now to find the slope of that line, let's plot 2 points on the line. So the coordinates of this point would be 0, 0. The coordinates of this point would be 2, 4. So slope would be 4 minus 0 divided by 2 minus 0, which would be basically 2 meter per second square, provided that the provided that the units are in SI. Now next we want to calculate the acceleration between 2 to 8 seconds. So acceleration between 2 to 8 seconds is uniform. Okay, because between 2 to 8 seconds the graph is a straight line, a single straight line. To find the slope, okay, so we need to pick 2 points whose coordinates can be represented. This point will have a coordinates of 8, minus 2. Now the acceleration is given by v2 or y2 minus y1. Okay, this is like x2 y2, this is like x1 y1 divided by 8 minus 2, which would be minus 6 by 6, which is equal to minus just a minute, minus 1 meter per second square. So it's quite obvious that the accelerations are not the same. The body is basically undergoing non-uniformly accelerated motion between 0 to 8. But if you look between 0 to 2, we can say it's undergoing uniformly accelerated motion. And we can also say between 2 to 8 seconds, the body is undergoing uniformly accelerated motion. But between 0 to 8, the total motion is not uniformly accelerated motion. Okay. Now, they can ask at which time the velocity is maximum. Basically, it's quite visible here. The velocity is maximum at t is equal to 4 seconds. Okay. So this is a kind of graphical problem that they can ask. Okay. And a few more problems, example problems we'll discuss at the end after we have a little discussion regarding motion under gravity. That's it for this video. We'll meet in the next video again.